I'm Dr. B, your chemistry teacher, and today we'll be talking about Hund's rule. All right, Hund's rule. I'm sure you have been hearing about Hund's rule. The theory, what it's talking about, and everything. Today, I'm going to take us through what Hund's rule is all about. But do not forget that as part of your contribution to this class, you have to share, you have to like, you have to make comments, and most importantly, you have to subscribe. Now, you can also send these videos out to your colleagues and tell them to subscribe. Alright, so you simply just need to type in Dr. B Science Classes. Dr. B Science Classes. Even on my Facebook page is Dr. B Science Classes. Once you type Dr. B Science Classes, you will have it up. Subscribe, and in the Facebook, you need to follow, and that's all about it. And once the videos are made and uploaded, you'll get a pop-up notification. All right, so we are going to talk about Hund's rule. And what is Hund's rule all about? I want us to know that at this point, I wouldn't want to start stating the law, the Hund's rule itself, because it might not make any sense. But to make this class very simple and easy for you and I will have to just break down by explaining what Hund's rule is all about. I want us to know that Hund's rule can also be differently called. Okay, it can be called the Hund's rule of multiplicity. Okay, Hund's rule of multiplicity, and this is just a definition, a name that defines what its explanation is all about. Do you know that the arrangement of electrons in the various orbitals of the various subshells is not just done like that? You must have seen things of this nature where these represent various spins. These represent various spins. Do you know that you don't just wake up one day and begin to arrange spins in various orbitals just like that? There is a rule that governs the arrangement of various electrons in the different orbitals of different subshells, and that arrangement, that rule that governs that arrangement, is what we call the Hund's rule. But what does the Hund's rule talk about? The Hund's rule simply say this, that for every orbital, especially degenerate orbitals, and what I mean by degenerate orbitals is simple: orbitals with the same energy. That is degenerate orbitals, orbitals with the same energy. And the Hund's rule say, for degenerate orbitals, orbitals with the same energy, if you want to arrange electrons in there, you must first start with singly arrangements. That is to say, electrons must fill these particular orbitals in singles, 1 1, before you now double. You cannot just arrange by doubling electrons first and then you now leave other orbitals empty. It's saying that, look, if you must arrange electrons in the various orbitals, especially those orbitals with the same energy, the degenerate orbitals, you must first do what? Pass through what we call singly occupied orbitals before doubly occupied orbitals. So you must first arrange them single before you can now double them. And if you must do that, you must understand that in the single arrangement of these electrons, the electrons must do what? Maximize what? Maximize a parallel spin. That is to say, the electron must do what? Be in a parallel spin. They must have the same orientation in terms of spin. That is just the explanation of what the Hund's rule. Simply, let me repeat myself. If you must arrange electrons in degenerate orbitals, that is orbitals with the same energy, especially like the p orbital, where we have the 2px, 2py, and 2pz. All the orbitals have the same energy level at the 2p orbital of its subshell. If you must arrange electrons in this kind of orbitals that have the same energy, they are degenerate, you must first arrange them by singly occupying these particular orbitals before you now double. If you must double, you must make sure that even at the first, the singly occupied orbital, the singly arrangement, the dropping of 1 1 electrons, the electrons must do what? Have the same spin. They must have the same orientation, the same arrangement. There must be a parallel spin. Alright, I'm going to explain that when we start doing some examples. But what you must note from here is that the Hund's rule is targeting the ground state energy levels, the lowest energy level, the most stable electron configuration. And that is why it simply says you must understand that the ground state energy level is in play. That is the most stable configuration. You must also understand that it must the Hund's rule must apply only to what? Only to degenerate orbitals with what? The same energy. Now, but what is the relevance of the Hund's rule? Because it's not just about telling us that arrange electrons by putting them in singles. You must understand that even in their singles, they must have the same spin. That is, they must have what? A parallel spin. It is not enough to tell us that. But what is the relevance of the Hund's rule? Hund's rule is important in chemistry. And let me tell you just one reason why it's important. The importance of Hund's rule is that it helps you, okay, to be able to determine the electronic configuration. I can just put it, it helps you to determine the electronic configuration, okay, of the most stable configuration, that is the lowest energy of electrons, of atoms and of molecules. Okay, that is it. If you are able to understand the Hund's rule, you'll also be able to determine what? To determine the electronic configuration of atoms and molecules, especially those that exist around the degenerate or levels, those with the same energy. So if you are not able to understand Hund's rule or the Hund's rule of maximum multiplicity, you will not be able to do what? To determine the ground state electronic configuration of atoms and molecules, especially looking at what? Looking at the most stable configurations or the lowest energy configurations, as we said. So if you want to be able to determine the ground state electronic configuration of atoms and molecules, you must understand the Hund's rule in terms of its multiplicity and in terms of the filling of the various electrons. Now let us take a look at what we have here. Do you know that this is the 1s, 2s and 2p orbitals? Remember that in the orbitals we have the s orbital, we have the p orbital, we have the d orbital for the transition metals, we also have the f orbital, right? And you go on and on and on, but the most ones that we know are the s orbital, the p orbital, you have the d orbital, you have the f orbital. All these are orbitals, and all these orbitals that you see here have degeneracy. They have the same energy. For the p orbitals, like we have the p, x, y and z, they have the same energy. They are degenerate. Even in the d orbitals, they are degenerate. Okay, so if you must understand, or you must be able to calculate the lowest energy electronic configuration of atoms or molecules, you must understand how these particular subshells have to be filled in terms of what? Occupancy of electrons. And take a look at this. The 1s orbital has 2 electrons, and in the 2 electrons, they are what? The spins are different. It must be so. This spin is minus half. This spin here is plus half. And this is the way you must maximize the unpaired electrons, okay, in these various orbitals. There must be a maximization of unpaired electrons where you can be able to have parallel spins in terms of the filling of the various orbitals. Now, if you take a look at the 2s orbital, because this will begin with 1s2, this will go with 2s2. That is the normal configuration. You have 1s2, 2s2, 2p6. That is the normal configuration. So, for the s orbital, there must be 2 electrons filled with arrangement such that there's a positive spin and a negative spin. The same thing will happen here, where you have a negative spin and a positive spin. Alright, now when you come to the p orbitals, ordinarily one will have felt that this 3, 1 should be in here to make it 2. And then this is 1, this is 0. But that is not true. This is where the Hund's rule play its role. The Hund's rule say this 2p orbital have px, py, and pz, and they are degenerate in nature. That means they have the same energy, and if you have to fill them with electrons to be able to calculate the ground state electronic configuration of the atom or the molecules to which this belongs, you must understand that they must be singly occupied before doubly occupied. And the singly occupied must occupy with the same word, power spin. So that is why you see they are singly occupied and with the same power spin showing up. And this spin is plus half, plus half, plus half. If you take a look at what you have here, this is correct. For the 1s2, two spins are coming in here, and the two spins are showing what? Are showing the same half and minus half. This is half and minus half. Correct. Here, there are 3, 1, 2, 3. This does not obey the Hund's rule. In the Hund's rule, they must fill the 3 in singlet before you now have doublet. But here we begin with doublet, and that is why we are saying this configuration is wrong. It disqualifies, it goes against the Hund's rule. So this is wrong because this is showing half and minus half. Why this is showing half, and what happened here? You were supposed to do what? First singly fill this, and if you singly fill this, there will be no doubling here. And in that case, this configuration is wrong. How about this? This is 1s2 and is correct, half minus half. This is 2s2 and is correct, half minus half. And here, this is 2p. Now in the 2p, this x, y, z, do you know that there are 3 electrons? Fine. And the 3 are filled. Good. But the problem we have here is that this electron is filled wrongly. There is no what? Power spin. For the singlets, there must be power spin, and there is none. Look at, this is half, this is minus half, and this is half. This is correct, this is correct, this is wrong. And if you follow Hund's rule, you must first do what? Arrange them in singlet and in power spin, the same spin direction. This is supposed to be what? Supposed to be a plus as well. And this configuration is wrong. Did you see the beauty of what? Of the Hund's rule? Now, believing that we have understand this, let us introduce an example and see how that can go well. Let us take an example looking at carbon, for instance. Let's see carbon for instance. Hope you know that carbon has 6 electrons. Okay, carbon has 6 electrons, and this is 1s2, 2s2, 2p2, 2, 4, 6 for carbon. How do we use the Hund's rule to be able to do what? To be able to fix in our electrons. Now, this will give us power spin and the down one. For the 2, the spins must be different, plus and minus. And this will also give us up and down, plus and minus. What happened here? This will give us, did you see? Now with this, there are only 2 spins, or 2 electrons. Now we fill them. For the Hund's rule, first you have to fill them what? Singlets before doublets. And if it's singlet, we must have this. We have filled the what? The 2px, the 2py, the 2pz is empty. So you have 2 unpaired electrons and 1 empty orbital. Now, at this point, you are very correct because you have been able to observe, to obey the Hund's rule. But if you had made a mistake of deciding to put the 2 in this way, then you will have been wrong. Because you do not obey the Hund's rule, where it says there has to be a singlet occupied before the doublet occupied, and the spins must be the same. Alright, there must be power spins. Okay, even if you had decided to have this, and then perhaps you jump this, and then you have this, you will have still be wrong. Even if you decide to write it in this form, you will have still be wrong, because you cannot jump the orbitals. They have the same energy. They will feel one after the other as they go. Alright, I'm sure you understood what we've done here. Now, what if we take a look? We decide to look at another example. Let's say we are looking at nitrogen. Nitrogen has 7 electrons. And this will 1s2, 2s2, 2p3. 2p3. So if you must do this, then this is 1s2, spin up, spin down. And then this is also spin up, spin down for 2 electrons for the 2s2. And here we have the x, the y, the z. We'll have 1, 2, and 3. There is no other way you will intend to write this. This is a half, this is a half, this is a half. This is a half, this is a minus half. This is a half, this is a minus half. There is no way you will intend to fill these electrons here that will be correct other than this way. You must make sure that they are singly filled first and the spins are what? The same. You must understand that the basic thing that describes Hund's rule is that they must be singly filled, they must singly filled through the orbitals that degenerate before they are doubly filled, and the spins of the singly filled must be parallel. That means they must be the same. Now, you can go on and on. If you were dealing with, let's say, fluorine, for example, fluorine is about 10, all right? So it's about 10 because oxygen is 8, all right? So you have fluorine also. So if you are using oxygen 8, that means that this will be what? 4. And if this is 4, let's write it. If it's oxygen, that is 8 electrons, 1s2, 2s2, and 2p4. Okay, so you have, of course, up, down, and here will give you up and down spin, and across this we'll have first singlet fill, and secondly you double. And you see that here is x, y, z. You see? So you see that this is the correct configuration because you have to first fill the singlets through the degenerate orbitals before you now do the doubling. Now, there is something you must note very well, that as far as the Hund's rule is concerned, the Hund's rule is based on the ground state energy level. It's based on the ground state energy level, and that's supposed to be the most stable electronic configuration level. And that the Hund's rule depends seriously on what? On degenerate orbitals, especially like the p orbitals, where it has 3 different orbitals with the same energy level. And the Hund's rule is also interested seriously on the arrangements of the electrons. Singlet occupied first. You must first arrange it by occupying with single electrons before you now double. And finally, it's also interested in what? In the parallel spin. There must be parallel spin in the singlet occupation, occupying these particular orbitals. There must be what? There must be spins that are parallel. That is the same orientation in terms of their spins. If these 4 things are taken into consideration, you will see that in understanding or in determining the ground state electronic configuration of atoms and molecules would have been very simple and very easy for you to handle. I'm sure that you have learned a lot today from this topic, Hund's rule. Until next time, do not forget to share, to like. Do not also forget to do what? To follow through my Facebook page, Dr. B Science Classes. Do not forget also to subscribe. As you share, tell them to also subscribe to